All right, we have a new topic today, enthalpy. The concept of enthalpy can be thought of as a measure of a chemical system's potential energy. Now, last week we kind of ended the discussion last week with defining two types of energy, potential energy and kinetic energy. Can anybody give me like a short definition of each? Tell me this. One of them has to do with motion. Which one?
Kinetic.
Kinetic energy has to do with motion. Potential energy, that's energy that's stored up, right? There's the potential for something to happen, but it's not happening yet. There's not any motion, okay? And once there's motion, then there's kinetic energy. So it's the rocket, the boulder at the top of the hill is potential energy. It's got all that energy stored up, and then when it rolls down the hill, now it's exhibiting kinetic energy, okay? So this energy that happens in a chemical reaction, we're still talking about energy. Last chapter was all about heat, which is a form of energy. This energy, the potential energy in a chemical system can't be measured directly, but what we can measure is what we refer to as the change in enthalpy. So change in enthalpy we represent by that. That means change in enthalpy. All right, change in H. And change in H is the energy change that accompanies a chemical or physical change. The energy change that accompanies a chemical or physical change. Now we're talking about chemical reactions, and we calculate change in H. Change in H is negative when a reaction is exothermic. All right, and then the opposite is true. Change in H is positive when a reaction is endothermic. So as we're doing these calculations, we'll be able to tell when we're calculating change in H if it's an endothermic or exothermic reaction based on the sign of our answer, right? Whether it's negative or positive. Make sure we know that. Whoops. Because we're going to have some problems that are going to ask us that, so make sure you know that. All right, so let's talk about enthalpy change, and the first thing we want to talk about, the first way we want to tackle it is using something called bond energies. All right, so this will be the first type of actual calculation that we'll do. And let's think about this reaction here, the combustion of hydrogen. When I combust something, what am I always, what's the chemical reaction? I'm adding it to, I'm combining it with what? Oxygen, right? So it's always something plus O2, and in this case it's going to yield 2H2O. All right, so we have the combustion of hydrogen. Since it's combustion, we know it's going to be exothermic because there's going to be heat produced, and we realize that already. But if we look at this from the standpoint of the bonds that are involved, so we're going to draw the Lewis structures for each of these compounds. See, every time you think something goes away in chemistry, it comes back, right? So you just can't learn it and dump it. You have to try to remember it. So at least we give you an opportunity to sort of refresh yourself, right? You can always go back. If you're fuzzy on Lewis structures, then go back, take a look at that. These are pretty simple. You'll know you did it correctly if whenever you total up the number of electrons, you have 8 around everything except for which element?
Hydrogen.
Hydrogen only has 2, right? So here's the thing, when we talk about bond energies, there's energy required to break these bonds, okay? And there's energy required to form the bonds over here, right? That's basically what has to happen as this reaction takes place. These guys have to break apart and then combine with the oxygen as it breaks apart and combine over here to form the 2 water molecules. So this is a good reaction to kind of easily see that, right? How they break apart and then attach themselves to the oxygen that broke apart. And so there's energy required in the breaking of each of these bonds, all right? And there's energy required in the forming of these bonds. And the nice thing is that somebody's already calculated what that energy is, all right? So we've got a table on page number, let's see, 420, page number 420. It has those listed for us. And just to clarify, when we break the bonds, we say that we're absorbing energy, and so energy is absorbed as these are broken, and energy is released as these are formed. Okay? And so this definition of change in enthalpy using bond energies looks like this. Change in H equals the energy to break bonds. Let's see. Bonds minus the energy to form the bonds on the product side. And just to define what bond energy is, to make sure we have that definition. Bond energy is the energy required to break a mole of a given type of bond. And so, like I said, we don't have to calculate these bond energies. They've already been calculated for us. We just have to look up the table, right? So we've got a small subset of various bonds listed for us, bond energies listed for us on page 420. It's the amount of energy required. The definition says required to break 1 mole of a given type of bond. And so that's why the units for bond energies is kilojoules per mole. Right? We've looked at the joule as standard unit of energy. So it's our standard energy unit per mole, since we're breaking 1 mole. Note that in general, the energy to break double bonds, it requires more to break double bonds than it does to break single bonds. Those double bond energies are all higher, and of course the triple bond's the strongest. So more energy required there. So the easiest thing to do here is let's just do a problem. And the nice thing about this particular problem is that it's using the exact equation that we've already kind of written down. So you're going to have to, in order to do these problems, you're going to have to remember your Lewis structures, right? You're going to have to be able to write these basic Lewis structures. They're going to be simple. We're not going to do any that are quite as complicated as we got before, but you are going to have to remember how this process works. So refresh yourself in that chapter if you're not remembering how that works, because you've got to write these down so that you know how many bonds that you have, right? So if we do a problem using this equation, it says use bond energies to determine the change in H of the following reaction. And that's an important point, the way that that's phrased. I only want you to use bond energies when I say use bond energies, okay? So if I just ask you in general, if I say find the change in H for this equation here, we're going to learn a better, more accurate way to find the change in H, and that's what I'm going to want you to do unless I explicitly ask for bond energies, okay? But they do explicitly ask for that here, and so it's basically you count up the bonds and you insert it into this equation here to get the answer. So change in H equals the energy to break the bonds. What we have here is we have 2 hydrogen bonds, right? So it's going to be 2 times 436 kilojoules per mole. Energy required to break the bonds, and also on this side where the bonds are being broken, we also have 1 oxygen double bond here, 498 kilojoules. So 2 oxygens double bonded together is 498 kilojoules per mole. And then you subtract out the energy to form the bonds. On this side, we only have 1 compound, but for this compound, we have 4 bonds between H and O. And so that's 460 kilojoules per mole. And just to note, if you think about it as a bond between O and H, recognize it doesn't matter what the order is, right? The bond between H and O, which is 460, is also the same value between O and H, right? So you can flip those around, that doesn't matter. Does everybody understand where I got these numbers here? And why I put the big number in the front? That corresponds to the number of those that we have, right? The number of bonds that we have. All right, so we can multiply that out. And it really corresponds to moles, right? We had 2 moles of this. We had 1 mole of this, or 1 here. Yes, we had 2 moles of this, but from the standpoint, because we had 2 hydrogens that were each with single bonds to the oxygen, the total was 4 moles of those bonds. And so that's what these numbers represent in the front. And so that's why our final answer, the mole on the bottom here, is going to cancel out. We're going to be left with a kilojoule value. So our answer in kilojoules is negative 470 kilojoules. That's what we'll get if we punch that in our calculator. They didn't ask us this, but based on what we've learned, when we get a negative value for energy, what does that tell us? That it's exothermic, right? That some of the problems we're going to do in a moment are going to ask us that. All right, any questions about how we did this? You got to remember Lewis structures, right? And once you remember those, it should be pretty simple. Just count up the number of bonds, add them up on this side, and then subtract out all the bonds that are on that side, and you'll get the total energy. All right, let's move on along. So let's talk about now, we talked about enthalpy change. I should have left that up here. Enthalpy change and bond energies. Now let's talk about enthalpy change and Hess's law. Using bond energies to find change in H is pretty simple, right? But it's not the most accurate way. Because it does not take the phase of a substance into account, right? We didn't care if it was a liquid or a gas or solid, any of that stuff. We were just looking at the bonds, and we said it takes this amount of energy to break those bonds. The reality is the energy is going to change depending on which phase the substance is in. And so that's why I said bond energies, you don't want to use those unless I explicitly ask you to use bond energies, because it's not the most accurate way to get it. But before we talk about what the most accurate way is, we need to define a term. We need to define what a state function is. And a state function is a property that is independent of path. What does that mean? I'll let y'all finish writing that down. All right, so let's say I'm writing on the board, right? And I'm writing and I make a mistake. Oh no, I need my, you have a question? Yeah, go ahead. I need my eraser, right? So the goal is to get the eraser that's over there. Okay? Well, I could do this. Just grab my eraser and come back, right? And that will have gotten the job done, right? Because the goal is just to get the eraser. But if I wanted to sort of be more exciting, I could like kind of do like this here and around and a couple of times like this, and then get my eraser, and then I could come and I could erase it, right? Well, here's the question. The goal of getting the eraser, was the goal of getting the eraser accomplished in both of those? Right? One was more fun than the other, right? Or made me look more dumb than the other. But the reality was I still accomplished the goal of getting the eraser. And that's the point with a state function, right? It doesn't matter what path you take. If the goal was to get the eraser, the goal was accomplished both times. I started off here, and I ended up over there. And so I accomplished, I reached my destination, right? And so Hess in the 1840s said, that's the way these bonds, that's the way this change in enthalpy works. Change in enthalpy is a state function. And so it doesn't matter how you get to the end of the reaction, as long as you start with the same products, and you start with the same reactants, and you end up with the same products, the change in H is going to be the same, however you get there, whatever path you take to get there, okay? And so that was what Hess introduced to us, and so we have a new equation that we came up with based on Hess's law. Before I write that down, let me state what I mean in a chemical way. When we talk about the goal is just to get to that end result. So Hess said, yeah, you could combine these together. You could combine 1 mole of CH4. This is the combustion of methane. So you could combine 1 mole of methane with 2 moles of oxygen, and you get 1 mole of carbon dioxide and 2 moles of H2O. All right? But you could also do it this way. You could decompose the methane. Do you guys remember what a decomposition reaction is? That's right. So this breaks down into C plus H2, and we need 2 of those. So that's the decomposition reaction, right? And over here, the opposite of decomposition is what kind of reaction? Don't make me dance again to get the eraser. What's the opposite of decomposition? Composition, that's a good guess, actually. It's not, but it's formation. Yeah, that would have worked, right? We're composing something. You're forming something. A composer forms a piece of music, so it's formation. So the formation reaction for CO2 would just be CO2 yields CO2. C plus O2 equals CO2, right? And so Hess said this. He said you could just take these two, combine them together, and you could get that. Or you could take these two and decompose them, and decompose this. Although O2, we wouldn't really break that down any further because that's how it naturally occurs. And then you take whatever we've broken down over here and you form each of these compounds on this side. And he said the energy that was involved in taking that path is the same as the energy involved if we went directly down this path. Okay? And so Hess basically allowed us to take the fun route to get the eraser, right? We do the breaking down first, and then we form, and then we get to our end result. All right? And so Hess's law, let's see. With Hess's law, we can use what we refer to as the standard enthalpies of formation. And there's a table for that on page 424. Since change in enthalpy is a state function, it doesn't matter what path you take, then you can use the table of the standard enthalpies of formation on page 424, and you'll notice something in this table that you don't have in the other table. In this table, you've got the phase of the object listed out there next to each one. So standard enthalpies of formation take phase into account, right? And so this is actually the more accurate way to calculate the change in enthalpy. One thing to note, when you have a substance like this, change in HF, this is, so the standard enthalpy of formation for any element, in its natural phase is 0. All right? So the change in H, the F stands for formation. The little degree symbol up there means that it's standard enthalpy of formation, or the enthalpy under standard conditions. Standard conditions would be 25 degrees Celsius, which is room temperature, and a pressure of 1 atm. But this is basically, this is Hess's law here. Hess's law says this. Hess's law says that for the reaction, if we have a reaction that we write down as this, little a big A plus little b big B yields little c big C plus little d big D, where the little letters represent the number of moles and the big letters represent whatever the compound is in the reaction, then we can say that change in H is equal to basically the sum of the standard enthalpies of the products minus the sum of the standard enthalpies of the reactants. So this is how I'm going to write that down. So that's Hess's law. What does this Greek symbol mean whenever we see it in an equation? Anybody know? You should have run across that, I think, at some point in your mathematical education. It's the Greek letter sigma, and it means sum of. It's like you might have it on your calculator. Some of you may see that on your calculator. It means take a sum of these values. All right? So kind of the shorthand way to write this here is that Hess's law tells us to take a sum of the standard enthalpy of formation of the products and then subtract the sum of the standard enthalpy of formation of the reactants. The reason I wanted to write that down like that is because I want us to understand that when we used bond energies, it's the reverse of that. Okay? So when we did bond energies, we basically took the sum of the reactant bond energies and we subtracted from that the sum of the product bond energies. So in Hess's law, the products come first and you subtract the reactants. It's the flip of that when we use bond energies. The reactants come first and you subtract the products. Okay? So that's a standard mistake that students make, and I don't want you to fall into that trap. So it's important that we point that out. All right, so I think this will be easy for us to see if we just do a couple of examples. Page 425. These are pretty straightforward and simple. It says, example 14.2, what is the change in H of the decomposition of hydrogen peroxide at 25 degrees Celsius? The only reason they told us at 25 degrees Celsius is because they're letting us know that it's standard conditions, right? So that means we can use the standard enthalpy of formation. And then they ask us, is it exothermic or endothermic? So the reaction is 2H2O2 aqueous yields 2H2O liquid plus O2 as a gas. And so since it didn't say explicitly to use bond energies, then we're going to use the standard enthalpy of formation. We're going to use that table on page 424. And so what we do is we take based on this, we take the products first. So we've got 2 moles of liquid H2O, and so it's going to be 2 times, we look up on our table for H2O in liquid form, and we see that it has a standard enthalpy of formation of negative 258.8 kilojoules per mole.
I think it's 285.
Oh, it is. You're right. Thank you. 285.8. And this unit is mole here. That's why our moles are going to cancel out. Plus O2. What's the standard enthalpy of formation of O2?
Just O2, right?
Is it on our table? Is it in our table, I guess I should say, on page 424? No. It's not? So how are we going to figure out what the standard enthalpy of formation is of O2?
Isn't it 0?
Where we wrote that down, right? We said if it's a substance and if it's a single element and it's in its natural phase, which this is, O2 is floating all around this, right? At normal temperature, it's a gas. So if it's in its natural phase and it's a single element, then the value is just 0 for that, right? So this is the standard enthalpy of formation for H2O plus the standard enthalpy of formation of O2 minus the standard enthalpy of formation, 2 moles of that, times the standard enthalpy of formation of H2O2 in aqueous form, and that is negative 191.2. Punch all of that in our calculator and we get a value of negative 189.2 kilojoules. Did anybody have any questions on how we figured that out? And I hope you see it's just as simple as looking up these values in the chart and making sure you multiply it by the number of moles of that compound, right? And then you just have to make sure which one that you're subtracting if it's on the reactant side and that you're adding if it's on the product side. Okay? Questions about that? Is anything unclear with that? Have we finished the problem? No. And I've had some of you guys, you get so involved in doing the math that there's a second part to the question and you don't answer the second part of the question on tests or on quizzes. What's the second part of the question here?
Was it exothermic or endothermic?
So which one is it? It's exothermic because it's negative. Because it has a negative sign, it's exothermic.
Positive is endo.
Positive is endo, yep. Now, like I said, this is more accurate than using bond energies because it takes phase into account. So make sure you remember that. If I ask you which one, if I were to ask you on a test which one's the most accurate of the two, you would say Hess's law. Finding change in enthalpy using Hess's law is more accurate than using bond energies. Or if I asked you why Hess's law was more accurate than using bond energies, what would you tell me? Because it takes phase into account. It includes the phase. All right. Let's do the next problem. It says, what is the change in H of the reaction given below at 25 degrees Celsius? Is it exothermic or endothermic? So we have another reaction. And this one is erase very lightly when I'm up here, otherwise the board starts moving. All right. So it's 2CO, which is a gas. 2CO as a gas plus 4H2O is a gas. Oops, I don't know why I put my parentheses there. 4H2O as a gas yields 2CH4 as a gas plus 3O2 as a gas. All right, so before I write down my equation this time, we're gonna go ahead and write down the standard enthalpies of formation below each one. Okay. So CO in gas form, negative 110.5. Right, kilojoules per mole. I'm not gonna write down the unit each time. H2O in gas form is, where are you?
Minus 241.8.
Minus 241.8, down at the bottom, the second row near the bottom. CH4 in gas form is negative 74.9. And of course, oxygen, that's its natural phase. It's just a single element, so that's going to be 0, right? So then the problem that the equation that we're doing, we write down our reactants first. And so we say we have 2 moles. The standard enthalpy of formation of negative 74.9, right? Plus our oxygen, which is 0, minus this one here. We've got 2 moles of that times negative 110.5 minus, because it's on the reactant side, 4 moles of H2O, which has standard enthalpy of formation of negative 241.8. So we punch all of that in our calculator, and we get a value of 1,038.4 kilojoules. Endothermic or exothermic? It's endothermic because it has a positive sign, not a negative sign. Is that simple enough? See how easy it is to plug those in? This is, like I said, this is where kids mess up. They forget to put the products first and subtract the reactants on when you're using the standard enthalpy of formation. Or they do that here, right? You do the reactants first when you're using bond energies and subtract out the product bond energies. Okay, So moving right along, let's see. I should have left the first problem we did up there. When we did the first problem here, which was the, let's see, it was the decomposition of H2O2. So we said this H2O2 aqueous yields 2H2O liquid plus O2 gas. We found out the change in H for this guy to be negative 189.2. Probably won't do grams. Negative 189.2 kilojoules. And we said the reaction was exothermic because it has a negative sign, right? Well, as it turns out, when you determine the change in H for a reaction, when you determine, which is basically the energy required for that reaction, you can add the energy to the chemical equation because it represents the amount of kinetic energy that's either released or absorbed in the reaction. So we can actually put this value in our chemical equation, and then, are you guys ready for this? We can do stoichiometric calculations with the energy in there now. Woo! Right? I know, every chapter you like, please bring stoichiometry back into this, right? Well, we get to with change in H. And so what it means is if it's a negative sign, it's exothermic. So at the end, it's releasing this energy, right? And so if it's exothermic, we're going to add this energy into the product side of the equation. Okay? If we'd done this and we'd gotten change in H is, I don't know, 2,000 kilojoules. Well, the positive side, we would have put that on the front here. Okay? So you put it on the reactant side if it has a positive value. You put it on the, you put it on the reactant side if it has a positive value. If it's got a negative value, you don't leave it negative. You put it here, though, with a positive value on the product side because it means it's releasing that energy, whereas over here it's absorbing that energy. Okay? All right. So let's do a problem. Let's just do that'll be the easiest thing to do with this so that it makes sense. Page 426 says, so we've got the same exact reaction that we have right here, and we calculated that it produces negative 189.2 kilojoules of energy. So if we have 500 grams of this stuff, 500 grams of this, how much energy is released in this chemical reaction? Well, whenever we did stoichiometry, remember we wrote this down on the board, right? Grams of A, moles of A, convert that to moles of B, and we can convert that to grams of B. So anytime we were given something in grams, when we did stoichiometric calculations, we always had to convert it to moles, right? Because the relationship between each of these guys in the equation are based on moles, not on the number of grams. So our first step when we do this is to calculate how many moles 500 grams is. So to do that, 500 grams of H2O2, we're going to have to figure out what? The atomic mass. So you guys should be able to do that in your sleep at this point, right? You go to the periodic table, look up the atomic mass of H, multiply it times 2, and add that to the atomic mass of oxygen, also multiplied by 2, and so you should get a value of 34.02. 34.02 grams of H2O equals 1 mole of H2O. right? So from that, we can figure out the number of moles of H2O. I said H2O. I'm going to say H2O2. The number of moles of H2O2 to be 14.7 moles. All right. So now that we know the number of moles, we can use the relationships in here just like we use for other stoichiometric problems. Remember that we said that this equation means that 2 moles of H2O2 equals, for example, 1 mole of O2, right? When we do stoichiometry, we say that 2 moles of this equals 1 mole of that, and then we can use this as a conversion factor, right? So then if we knew we had 14.7 moles of this, we could figure out how many moles of this we needed by using this relationship here. The same thing works with the energy, because this now that we have our energy added in, we can also say that 2 moles of H2O2 equals 189.2 kilojoules. So we have a new conversion factor that we can use to convert from one to the other, right? A new conversion relationship. So if we have 14.7 moles of H2O2, we can figure out how much energy that is by saying, well, we know that 189.2 kilojoules of energy is equal to, for this reaction, is equal to 2 moles of H2O2. And then we can get a final value of 1391. 1,391 kilojoules of energy would be released if we started with 500 grams of H2O2. So the first step, you calculate the energy using the standard enthalpy of formation. And then based on whether it's got a negative sign or a positive, we did that in the last problem. We found it to be negative 189.2. Then based on whether it's positive or negative, we decide if we're going to put it on the reactant side or the product side. Because it was negative, we put it on the product side. And then you use that relationship to calculate, to convert from the grams of one substance to the amount of energy. That's basically what we did. We did grams to moles here, and then we did moles to energy using this equation. Or that relationship, sorry. All right. Any questions about that before we discuss our last topic? And there's not any dumb questions, guys. It's there's always people. I can tell by what happens on the test, right? That some of you have questions whenever we go over this stuff, but you don't ask the question, and you're not the only one that has that question, because there are others missing having the same issue on the test. So if you got a question, it's not a dumb question, right? There's someone else that's wondering about the same thing. So if you've got a question, please ask it. At a minimum, come see me after class, right, and get help with that. Am I blue in the face yet? Because I feel like I've been saying that until I got blue in the face. All right. Let's talk about our last concept today, which is activation energy. So whenever we talk about the combustion of a compound, you know, we saw this before when you combust methane, or I can't remember what it was. We had a combustion reaction was like the first thing we looked at today. But when you have a combustion reaction, you take some substance and you combine it with what? O2, oxygen, right? Oxygen. So combustion reaction is always whatever that substance is plus O2, right? Let me ask you a question. Is paper combustible? Oh yeah, right? You can't get your fire started in the fireplace, get your wood going. You'll crumple up some newspaper or something like that, right, to try to get it going, or get your charcoal hot on your grill or something like that. So yes, paper is very combustible. Well, guess what's floating all around the atmosphere right now? Oxygen's floating all around us, right? And it's coming in contact with this paper. So why doesn't this paper just burst into flames? Because it's coming into contact with the oxygen.
There's no heat right there.
There's no heat, right? And you're right. You've got to apply some heat to this paper to get the reaction to start. Now, what did we learn last chapter that heat actually is? Heat is energy, right? So we need some energy to get that reaction started. The reason it won't just happen when the two are touching one another is because there's not enough energy for it to happen. So when we supply that heat to it, we're adding the energy. We're adding the activation energy that's necessary for that reaction to be activated. Does that make sense? So we have to have some reactions. Some reactions are, they don't really, you just kind of bring the compounds close to one another and all of a sudden they will react because there's not a lot of activation energy that's needed to start them. But some, like as in the case with oxygen and paper, you're going to have enough energy to kick it off, right? So we're going to look at something called, look at some diagrams called reaction coordinate diagrams. And they tell us about the activation energy that's necessary for a reaction to start. And I'm going to show you two diagrams. And so on this axis over here, I'm going to put energy in kilojoules. Do that on both of these, energy in kilojoules. And for both of them, I'm going to put a mark for 200, 400, and 600, 200, 400, 600. Do that on both, 200, 400, 600. Oops. We're just going to do, I think I'm going to do this in the orange color, because I said the last class the orange was kind of hard to see, but that'll be good for these little dashed lines here. We always call them dotted lines, but they're not really dots, they're dashes, right? And so here I've got a reaction that looks like this. It's going to go up here, come down here, it's going to come out like that. And over here I'm going to have a reaction that does this, like that. All right? And this is the reaction coordinate. Remember, these are called reaction coordinate. You know, you're writing something down, all of a sudden it looks really weird. That doesn't look right. All of a sudden the COO in this looked odd in coordinate. What is that, right? So these are called reaction coordinate diagrams. All right, so this is our chemical reaction taking place, and here we have the reactants over on this side. We've got the products over here on this side. Same thing here. Reactants over here. And then what we end up with down here, the products. And so this value from here down to here, that's our activation energy. Okay? And then the difference in the energy that we start with and the energy that we end with, that's our change in H for these diagrams, okay? So for this diagram over here, the energy that we started with versus the energy we ended with is represented from there to there. line all across here so that we can see for our second diagram that that's our activation energy. So here's what you should be able to do. If I give you these diagrams, you should be able to tell me if your reaction is endothermic or exothermic, and you should be able to tell me what the activation energy is, as well as the change in H for that particular diagram. So let's see if we can figure that out. The change in H for this diagram, change in H based on Hess's law, is going to be basically your product's energy value minus your reactant's energy value. So for this one, we ended with 400 kilojoules, and we started with 200 kilojoules. So our activation energy over here is 200 kilojoules. I'm sorry, not my activation energy, my change in enthalpy. If I said activation energy, please forgive me. It's 200 kilojoules, and so then what, is this an endothermic or an exothermic reaction? Endo, because it doesn't have a negative sign. It's because it's positive, it's endothermic. All right, what about our activation energy? The activation energy on this one is the energy up at the top, 600, minus the energy that it started at, 200. So for this one, the activation energy is 400 kilojoules. Does everybody see that? So it's the distance from the peak. That's always going to be a positive value. It'll be the distance from the highest point to the start, minus the starting point. Okay, let's do the same thing for over here. Change in H is, for this one, the products ended at 200 kilojoules. Whoops, not equals, minus the energy that we started with, and in this case, we started with 500 kilojoules of energy. So this one is negative 300 kilojoules is our change in H, so this reaction is exothermic. Right? The ending energy value minus the starting energy value. And then the activation energy is the peak energy value minus the starting energy value, which was 500. So the activation energy for this one was 100 kilojoules. So if I gave you these two reaction coordinate diagrams, and I said, which one is the easiest reaction to start, the one on the left or the one on the right, which one would you say? Mm-hmm. Why? Exactly. This amount here is less than this amount here, right? It requires a lower activation energy. So this one will start easier. All right, so let's do one example in the book and we'll be done for today. It's page 426. Oh, 429, I'm sorry. Page 429. And it says, in a chemical reaction, the reactants start with an energy of 100 kilojoules. The activation energy is 500 kilojoules, and the change in H is 200 kilojoules. What is the reaction coordinate diagram for this reaction? So this one, they give us all the pieces, and they say, I want you to draw the diagram for it, right? So it's the reverse of what we just did. So we got to draw the diagram. We're going to put energy over here in kilojoules. Whoops. And we're going to put, this is our reaction coordinate down on the bottom there. And we know we've got a value of 200, a value of 500. So we're just going to mark them all off at 100. right? So our top part there is 600. This is 100, 200, 300, 400. Sorry if I'm squeezing that in a little bit right there. Hopefully you can read that. And so they tell us that it starts with an energy of 100 kilojoules. So we're starting here. This is our starting point. The activation energy is 500 kilojoules. So the activation energy is the distance from the peak to the starting point. So this thing's going to have to go all the way up to 600, right? So it's going to start there and it's going to go up to there. And then the change in H is 200 kilojoules. Well, change in H is the final energy value minus the original energy value. So if it's 200 kilojoules, then this has got to be where the reaction ends up, right? Because 300 minus 100 is 200. Okay? So it starts off there, and then it's going to come down to here, and it's going to level out off like that. So does everybody see how we found that? I mean, you could have done that mathematically, right? You could have said that the reactant, we start at 100 kilojoules. You know that activation energy equals the peak energy minus starting. And so they give us the activation energy to be 500 and some unknown peak energy, PE, we'll call it, minus the starting energy, which was 100. And so then we solve for PE by adding 100 to each side, and we know that the peak energy is 600. Right? So you could type that in. I mean, you could punch that in and figure it out mathematically if that's easier for you to do. But I think these numbers are probably small enough that we can just kind of do it in our heads, right? Just check it at the end. Always do that. When you draw your diagram, you can just look at the diagram now that it's drawn and easily see activation energy is 600 minus 100, 500, so verify that jives with whatever the problem said. And you can see that the final energy value is 300 minus 100, which is 200 kilojoules, and that's in fact what it said. Okay? And is this an endothermic or an exothermic reaction? Endothermic. It's endothermic because the final energy value was positive. So I'm glad. Was that you, Logan, that said that?
No.
Oh, that was Jed. Okay. So I'm glad we had someone else say something because I just remembered I got to write down the name, and that reminded me that I've got to take roll. Make sure there's nothing final to go over. Yeah, that's it. That's it for today. So, any final questions? Who's missing today? I know Lily wasn't going to be here. Is there anybody else missing? Cruz isn't going to be here. You guys see anybody else missing? Lily and Cruz?
I have a question.
Uh-huh.
So on the graph, like looking at it, the ones out of the three you've done, the one that was exothermic, the reactant is higher than the product, and then the other two, the product is higher than the reactant.
Right.
So can you tell by that if it's endothermic or exothermic?
Absolutely. Yeah.
Okay.
Because it's as long as you can. That's an easy way to eyeball it, right?
I have a
If
question.
this number's below, if this line's below this line, then you know it's going to be exothermic. Another question?
I had the same question.
Oh.
I kind of noticed that.
Yeah, you're right. Yeah, so you can kind of eyeball these graphs when you draw it correctly. And you can tell as long as this value is higher at the end, you know it's going to be an endothermic reaction. All right? All right, y'all have a good one. Like I said, please stay and ask questions if you're confused about anything.